This orientation training video was a part of the Real3D measurement tips and best practices webinar.
The question came up earlier when we were covering the slides in this webinar on Real3D measurement and talking about tips and best practices. Are all of these measurement types that you're showing us available on all of the video probes? And the answer is they are only all available on the Mentor Visual IQ Flame handset. If you look in the column under MVIQ Flame with 3.5, yes, the Analyze Y-A, all of those measurement types are available in those. So the Analyze has every measurement type, including blade tip clearance and auto repeat, which are new. We just released them in 3.5. So the MVIQ flame colored handset with 3.5 software that was just released has all of the measurement types available. If you move to the next column, the Mentor Visual IQ gray handset, the last software that was released for it, 3.18, there are no software upgrades planned for that platform. So yes, if you have an Analyze, you can get everything from length all the way down to a measurement plane. And you'll notice it's not going to have blade tip clearance or auto repeat. So now both on the flame and the gray handset, there are three varieties of those. There's an inspect, which is a really good system that has everything you need for excellent inspections, but not all of the high-end capability because maybe you're not measuring. Maybe you don't want a touchscreen. So if you do want to measure though, and you get the standard measurement package on an inspect or a touch, you will have all of those measurement capabilities from length all the way down to depth profile. It's the same on the flame or the gray. If you want to have area depth profile or measurement plane, those are apps that you can add on to the flame or the gray when you choose the inspect or touch platforms. So a couple of different iterations in the Mentor Visual IQs.
Then when you get over to the XL G3 and the other XL types like XL Go, XL View, XL Flex, you can read the tables. They're fairly explanatory.
Another question that came up is around point-to-line measurements and when using them on measuring missing material or erosion on the trailing edge of an HPT blade in an RB211 jet engine. What would have been done in the past and still can be done today, if this is the instrument that you have, is add a point-to-line measurement where you're going to place the cursor, in this case on the tip of the blade, establish that tip of the blade, then up on the leading edge, place your third cursor, and this is going to let you measure from where that blade tip would have been, and it's measuring it up to that point. In this case, we may go down here. It depends on where you want to interpret. If you're going to have to blend, maybe you would go somewhere in this area, or if you're just wanting to know the actual missing material, you can skew it down to where the actual tip of the main material still remains, somewhere in this area. So you see it's masked in yellow, which is questionable data. We can overcome that. I'll show you how in a moment. But you're missing somewhere around from where the tip of the blade was up to the leading edge where the damage stops, somewhere around 56 thousandths. You'll see how the point to line icons are laid out. On the 160 thousandths, that's the distance between the two cursors on the tip of the blade, and from that imaginary line up to the missing material is 56 thousandths. Then you could repeat that by activating these cursors and spinning them over, doing the same thing on the leading edge, and putting this one down here onto the data that's material that's normalized. So let's get them back to where they need to be. I want to get us into the general area where we want to measure, but you see there's a lot of unmeasurable data that's out there. Presents its own set of problems, and that'll happen with stereo or 3D phase, and I'll show you how to work with that. So then we're missing somewhere on this tip of the blade something like 84 thousandths, 85 thousandths. You know, if I get right out to where I want to place the cursor, some 84, 85 thousandths. So that's how you would do that with point to line. Another way to make this measurement instead of using point to line would be to add a measurement plane. This measurement plane is going to establish a mathematical plane based on these three triangular cursor points. And you'll notice that there is a green surface mask. All of the pixels that have a Z value, or a distance from the camera value, that is very close to the mathematical plane established by those 3 points, are going to be masked in green. So you want to maximize the green planar data around the area you're going to be measuring. Don't get way out here, you're taking the curvature of the blade into effect. Get out here close to that missing material and maximize your surface mask around there as best you can. And so what I'm dealing with is a noisy image, meaning a noisy point cloud. And I was asked that question also, what is the difference between a good and a bad point cloud? Bottom left, touch views, point cloud, touch point cloud. I'm now looking at the full point cloud. I can tap that toggle button on the bottom right. If I tap that toggle button, tap, tap, it clears the screen. Now I'm putting 2 fingers on the screen and squeezing out. I'm putting 1 finger on the bottom of the screen and rolling the image up. And now I start to see these mountain peaks. Each place you see a peak, those pixels didn't get reliable fringe pattern data on them. And those pixels are pulling the point cloud up above that measurement plane. So you'll see that all of the pixels that are masked in green are very close to that reference plane. So I have a noisy image, and it's the only image I have to work with right now. So let's make the best of it. I can now go to my full image for placing my cursors and bottom center touch, add measurement. There, instead of point to line, I'm going to use area, and I can place 24, up to 24. And believe me, if I'm going to pass or fail an asset, I'm going to use as many as it takes to make this measurement precise. There's my first cursor. I pressed enter. I can now move my second cursor. Press enter. I generally stop touching the screen at this point when I'm placing cursors. It's too easy for the thickness of my finger pad to inadvertently change cursor's value. So I'm using the joystick and the enter key. And for the sake of this exercise, I'll put 1 more down here at the tip of the blade. Okay, then I'll place 1 more out where I thought the tip of the blade may have been, and I'll press done. And you see the dotted line. There's 1 that's down by the tip of the blade and 1 that's generally following the leading edge. To get that to exactly line up, I'll touch that cursor out on where the tip was, and watch if I move it up or down, that dotted line will actually get closer or further from the tip. Right now I'm fairly closely following the tip. Now I'm going to move it out to the left. You see it's going left and right, so I want it to follow the tip of the blade. Correction, I want it to follow the leading edge of the blade. And also, this is when that mask could get in my way. So I'll touch the global menu, go to settings. In the measurement annotation on the lower left, I can go to the 3D surface mask, bottom right. I can show and save it. I can hide it, or I can show it. So I'm going to hide it for now. So I want to hide it. Touch the back key. So you don't see my surface mask, I just hit it. So now I'm going to use my joystick and move that cursor that's active. You see it's active because it has a bold blue circle around it. I'm moving it to get the tip of the blade. And maybe I need to move this cursor down somewhat because it may not be actually down on the exact tip of the blade. That is pretty close right there. And then I'm looking at the dotted line, the reference line along the leading edge, and it looks like it's fairly lined up also. What I'm dealing with now is a leg that is leg 1, meaning the material missing along the tip of the blade out to the leading edge, of 93 thousandths. Leg 2, where the tip of the blade would have been on the leading edge, and from there up to the leading edge, normal material missing 61 thousandths. And so that area is 2.6 thousandths of a square inch. And if that blade tip was there, it would be approximately a 74-degree tip angle. So that's how you would use the measurement plane and the area measurement to give you information about missing material. One of the measurement types that people indicated quite a bit was a measurement type they were having to do frequently was blade tip clearance. And in this case, here's a stereo, or actually a Real3D stereo image where somebody on the left-hand side had placed 3 points to establish a mathematical plane on the shroud at the top of the image, and then placed a 4th point on the tip of the blade. And if you recall, what I indicated was crucially important was that each cursor on your side, meaning the left side of the image, and let me get them all the way through, I'll get to the first cursor. So there's the first cursor. Look in the 3x zoom window at the bottom where the crosshair is. Look at all the real estate color. You'll see a little black area up in the top right-hand quadrant of the cursor. And look at where the tail is hitting the area just below the blade, and it looks like a good match on left and right. I will press the enter key. I'm looking around there, and the references that I have are the landmarks on the blade tip just below the crosshair. You'll see some rises just to the right. You'll see a cooling hole just below it. Looks like a fairly decent match. I'll look at the third cursor. I see a horizontal line just below the crosshairs, and I'm looking at all the real estate, the pixels that are surrounding that cursor, to do everything I can to verify pixel matching. And then I'm looking at the tip of the blade, and the call is 38 thousandths. That's your job as the inspector with stereo, and you don't have the ability to see the 3D data behind this. You have to move the cursors around quite a bit just to be able to interpret what that data is telling you. The 3D data, it's there. Each pixel holds 3D information, but you can only determine that 3D information at the placement of cursors. So here is what is uniquely and fundamentally different about Real3D. A couple of things. I'm going to double tap the right hand portion of the touchscreen, and I'm going to now toggle the soft keys, and I could undo this, I could change views. I'm going to select views, and you see that I can look at my normal view. That's what I'm looking at now. I can look at only the point cloud, or I can look at the white light image on the left and the point cloud on the right in the split point cloud. I will select, for the sake of looking at this full-size point cloud, you can see the magenta plane. The 3 points of the mathematical plane are on the far left, up underneath the blade at the top right, and underneath the blade on the bottom right. The fuchsia colored dot is on the tip of the blade. So now I'm going to double tap the toggle key to clear out my screen. The blue box around the image is an extension. It's a reference plane that is created and relevant to that measurement plane. So when I rotate it and get a single blue line, I'm looking directly across that measurement plane of those 3 cursors. And now, 2 fingers, I can rotate it one way or the other. I want to get it about as flat as I can, because watch when I rotate it. Now I'm looking across that plane, and somebody once said, we have a problem. That cursor on the right is not on the shroud. And as a matter of fact, if I rotate it, that horizontal black line is the point cloud of the data that's on the shroud. And if I zoom significantly in on it and pull it up on the screen with 2 fingers, this is indicative of what I call a clean point cloud, because there is very little, if any, noise in it, and that noise is certainly not anywhere near the cursors that I'm measuring on. This one may be close, so I can move it out here, get it off of it, but that is a clean point cloud. That measurement plane looks like the surface of that shroud. But the real problem is this cursor here that I just touched and made active is on the blade and not on the shroud. So I'm going to go back and show you what we're looking at. White light image on the left, point cloud image on the right. If I were to move this cursor that looks like it's under the blade and out on the shroud, if I were to move it up, I moved it up about 4 pixels, and you notice it's around unmeasurable data. Any stereo system, when you're measuring around unmeasurable data, it is highly suspect. And so you see that I'm not even getting a measurable point there. If I continue going up north with that red cursor, you can now see what's going on in this point cloud, where I'm now getting, instead of 32 thousandths, I'm getting 61 thousandths. And that image there is a money shot. You see, I have no shroud sticking up above or below the plane of the point cloud. It is a perfectly clean point cloud. The tip of the blade is being measured very accurately. And I'm going to tell you that that image there, or that measurement there, is a 61 thousandths of an inch, 61 thousandths of an inch, plus or minus a thousandths or so. That's what you have to do at the point cloud. That is how you're going to verify the system is working correctly. Another question was asked around, are there any tips to measure depth in a weld bead? And yes, here's an example of a weld bead, and because of the apparent curvature, I would say this is likely inside of a tube. It looks like there is a strike point there on the right-hand side of the weld reinforcement. So let's look at several ways to measure depth here. If I add a measurement, I have several depth types. I have depth, depth profile, and area depth profile. Let me show you how you might use depth first. So again, I'll establish a mathematical plane with 3 cursors. I'm following generally the heat affected zone, and I will put a 3rd cursor pointing it down the longitudinal axis of the pipe. Now again, if you look at that surface mask, and let me exaggerate this, I'll move this out of the way for a moment. Pay no attention to that 32 thousandths, I'm not ready. I will exaggerate. You see the surface mask is separated. All of that green data is close to the plane, so everything that's not green is above or below the plane. So when I start bringing this cursor back down the pipe floor, get it closer to that other cursor on the left, I'm starting to get down to the area that I can measure a plane that's flat across the surface of the material and not above or raised above the surface. I also want to have this pointer going down the longitudinal axis, and it actually looks like it should probably go somewhat to the right a little bit. You see I can move the cursor in the point cloud, and now let me look and see if I'm pointing down the pipe flow. A lot better. And you also see my surface mask down at the bottom has closed up. So now with that, I can again move the cursor in the point cloud, or I can move it in the white light image. So if I want to move it in the white light image, I touch the left side, make it active, and I can now look at the reinforcement height there, and you can see it's probably somewhere around 28 thousandths of an inch, and you're wondering how I'm getting that and what that blue mask is. Remember, the green mask is data that's very close to that measurement plane. Anything that's currently masked in blue is 28 thousandths of an inch, positive number, so that's above that plane. Let's look. In the point cloud, I'll make it bigger so you can get a better feeling for what's going on here. So there's my blue separation, that blue surface mask, that's 28 thousandths of an inch from that magenta plane there. So if I look straight across that plane, which is represented by that blue reference line, the reference plane, You can see that the green surface mask is data that's very close to the plane, and the blue is surface mask is all data that's 28 thousandths of an inch away. So now I can start rotating it. Now I'm looking into the weld, and you can see that I'm somewhere around the highest point on that. So if I maximize it to where they meet, somewhere in there, 28, 29 thousandths of an inch is that reinforcement's height there. You have to be careful because there is what some people refer to as high-low. So if I were to take this cursor, move it off of the reinforcement to the other side of the pipe, go down below the toe, and you can now see that I actually have an offset, meaning a high-low. And a high-low means that my pipes are not in axial alignment with each other. So where my measurement plane is on the left, I can look straight across it. And you can see on the right that I have a separation 14 thousandths of an inch above the plane. That's this point here. You know, if I were to take it up here just to exaggerate it, that's 47 thousandths of an inch, but that's not where we were. We wanted to be down in the pipe floor, somewhere in this area. Yeah, I have about a 14 thousandths of an inch of high-low. So that's one way to look at this. When you become disoriented or lose your placement in the point cloud, touch the bottom right-hand cursor or soft key and it will toggle and you can reset the point cloud to reorientate yourself. Then I can go back to my views, I can go back to my normal image, and now I want to know what the profile of that weld is across the entire weld. So to declutter the screen, I'll delete that measurement. I will use an additional measurement type. I can use depth profile, that's one slice. I can use area depth profile, and that can take several hundred slices. From the cursor on the left to the cursor on the right, it's drawing a straight line between those two cursors, and it's calculating the Z path between them. When I touch the bottom portion onto the pipe at the bottom, that radius curve that's calculated at the top is going to be replicated at the bottom. And you can see that it picked that strike point as the highest point on that entire weld. And you can see now there's that one slice that was used. And it looks like it maybe is not actually aligned. So I will move these cursors to get it going straight up or down the pipe floor. It may be easier if I go into the full point cloud to do this because I can get a better view of it, and I can also actually move these cursors. And that needs to go down somewhere in here. This one looks like it needs to come up into this zone somewhere. And now, yeah, still getting 39 thousandths of an inch. Several ways to measure the depth height of a weld bead and also determine the high-low. Now, the last two images that we looked at had examples of very clean point clouds. The first one of the tip to shroud clearance on the power turbine, very accurate measurement, very wrong measurement because of the cursor placement. When I received this picture, the man was so excited about the technology that he was exuberant and said, "Wow, look at this picture. What do you think?" I said, "Let me tell you what I know to be true. You were measuring with a black tip up in the top right corner. It is serial number 24. One of the cursors, or all of the cursors, are 1.09 inches away from the camera. And then you're doing a point to line measurement. I can see that in the top left corner, and I can also see how the cursors are laid out. And I can also see in the value window that the two cursors on the leading edge on either side of that, this was actually filed out for training. The two cursors are separated 317 thousandths, and from that imaginary line, there's 120 thousandths of what some people call depth. It is actually a distance from that line. It's always perpendicular I said, why is that line so curved? Do you have any idea? Did you look at the point cloud? And the answer was, no, I have not looked at the point cloud. So the first thing you do on any image before making a determination of good or bad is go to the point cloud. That's what he thought he was calling, and this is what he was actually getting. He was actually getting this measurement here, where if you look on the bottom right, that cursor there is so far behind the plane of the blade because it caught reflections, meaning the fringe patterns reflected off of that edge, and it looked out into the distance and saw that data back there. It was, I think, exacerbated by having another blade right behind it. But this cursor actually needed to be up here in this area. So now instead of 120 thousandths, that's 95, but let's look at the white light image. You know, my other clues were that the dotted line, the reference line, and you see the surface mask, which he didn't have at the time, they were something like this when I got the image, and you see that line that appears not to be perpendicular to the measurement line. So I'll readjust these cursors, press the enter key for the next cursor. That one looks fairly good on that depth or distance from the line. And this first cursor, actually, if you look in the zoom window, probably needed to be up in this area where you probably blend out that damage. Maybe, maybe not. You're the turbine person. You make that determination, but you see it's wide right at the top and into the material at the bottom. So I'll take a look at this and get it out onto what is the leading edge of that blade. And so now, feeling much better with 101 thousandths instead of 120 thousandths. And if you look at the point cloud, this did nothing to improve the point cloud quality. I still have that noise beyond the plane of the blade. You can see it shooting off to the right. And there's no way I would tell you that that measurement there is correct. I would say, can I get any closer? Can I get more magnification? Can I get the camera so close to that surface that that groove or that grinding point is filling up half or more of the screen to get a lower MTD? So that's an example of a poor point cloud and poor technique, unfortunately, all in the same image.